Hi friends, welcome to this session on insertion sort, and here we will discuss over the intuition of this algorithm. We'll also see the dry run for this algorithm and we'll also implement in code in Python this particular algorithm. So let's start. So let's say we are provided this particular unsorted array X where we have 5 elements, and since this is a zero based index data structure, so we have indexes starting from 0 till 4. Now the insertion sort, how does it work? It works by dividing the given unsorted array into two parts. One becomes a sorted part, the remaining is the unsorted part. And the intuition behind this particular algorithm is it takes the first element from the unsorted part, and then it works out to look out the appropriate position wherein this particular element needs to be inserted in the sorted part, and hence the name insertion sort. So let's begin with the dry run. So in the first go, this algorithm will take the first element of the unsorted part to be belonging to the sorted part, and the rest would be taken as belonging to the unsorted part. So herein it is divided into two parts. This is the unsorted part, and this is the other one is the sorted part. All right. So now how does it start is in the first iteration, or what we will now do is we'll repeatedly take the first element of the remaining unsorted part, and we will initialize, and we will assume that this element needs to be inserted at a position. So we will initialize this value index where this element will be inserted. We'll initialize this with the value of itself, that is 1 here for this particular case, since this is the element at index 1. And now we will compare this element with every element of the sorted part, and upon comparison we will devise whether it needs to be swapped or it needs to be compared with the yet another element in the sorted part till we reach index 0. All right, so in the first go, what it will do, we have X index to insert, that is we have assumed or we have initialized the index to insert value as 1, and X of 1, the value we have is 10, that is the element 10 we are looking into, and we compare it with the first element, or from the back. Basically this is the first element from the back of the unsorted part, and we see how 10 compares with 30. So 10 and 30, 10 is less than 30, so we will swap the values here. So now this swapping would happen, and the list would become like this. At the first position we have 10, then we have 30 since we have swapped these values, and rest of the list remains the same, 20, 50 and 40. All right, now this was the first go. Now in the second iteration, so at every iteration we are selecting one element, the first element of the remaining unsorted portion. So here we have the sorted portion as this now, right? We have moved one more element further in the sorted portion, and we have the unsorted portion as this. This is unsorted, and this portion is the sorted one. Now in this iteration, we will take this element, the first element of the unsorted part, and we will take that and initialize the value of index to insert is equal to the index of the element that we have chosen. that is index 2, that is the value 2. Now we'll compare x index to insert with, we'll compare it with the first value from the back, that is with the value 30 of the sorted part. So x index to insert is value 2, x2 is equal to 20, and how does 20 compare with 30? 20 is less than 30, right? So since it is less than 30, so we'll swap these values here. So at this point, the list that we have, that becomes like this. We have 10 at the start, now we have 20, then we have 30, then we have 50 and 40 at the last. So now, yeah, so now what we will do is, we have still one more iteration to go in this particular iteration of this element. Now we have 20 and we have 10, and also we will change the index to insert value to the one which has been updated, that is the value 1. Earlier it was 2, index to insert was 2 earlier, now it is 1. So now we'll compare this particular element with the other element of the sorted part. So which is, how does x index to insert, which is x of 1, which is equal to 20, compares with 10. Now 20 is less than 10. No, it isn't. So the order remains the same. So this is and now since we have reached the 0th element of the sorted portion, this was the sorted portion earlier of the sorted portion. So now we basically come out and do the next iteration. That is, the next element from the unsorted part would be selected now. So far we have this list. We have 10, 20, 30, 50 and 40. And what is the sorted part now? We have sorted part as this, right? And the unsorted part is the remaining one. Now we'll select the first element again from the unsorted portion, which is 50, and we have indexes as this. So the index to insert is equal to 3, that is the initialized value to be initialized. Now we'll compare 50 with 30. Now how does 50 compare with 30? Is 50 less than 30? No. So we'll compare it with the next value. How does 50 compare with 20? Is 50 less than 20? No. We'll compare it with the next value. Is 50 less than 10? No. So there is no swapping that needs to be done, and we will keep 50 as it is here. So the index of to insert value 3 is not changed and remains same. In the next iteration, now we have the sorted portion as this. Sorry. So we have the sorted portion as till this point. Now we take the first element of the unsorted part. Now indexes again, let me put it over here. So index to insert is equals to 4, and now we'll compare 40 with 50. How does it compare? Is 40 less than 50? Yes, it is. So we'll swap it, right? So we will have now this particular list shown up like this: 10, 20, 30, 40 and 50, right? And herein we have the index to insert, that is the index wherein the element is to be inserted, as the value 30. Now it's been updated here, right? Now 40 compares with 30. So is 40 Is 40 less than 30? No, it isn't. So now tell me, at this point in time, since we are comparing it in the sorted portion, now herein, if the latest element of the sorted portion we are comparing with is not greater than the one which we are searching to insert, right? So do we need to go any further? Because if 40 is not less than 30, 40 is not going to be less than 20, 40 is not going to be less than 10 as well. So at this point in time, you can stop this particular iteration of the sorted part, right? That would be some more an additional optimization on top of it. So we get to know at the end of the fourth iteration that we have the sorted list as 10, 20, 30, 40, and 50. So that comes out to be our sorted list. So this is how the intuition of the insertion sort algorithm is. Points that we understood from here is like if the array is of length 5 or the list is of array of length 5, the unsorted list, then we need to do 4 iterations, because in the first iteration we assume that okay, the first position itself is as a sorted is as a part of the sorted is a sorted part rather, and the rest is the unsorted part. So we need to compare each of these elements of the unsorted part which are 1 minus also, which are the number of elements in the unsorted list minus 1, right? So that those are the number of iterations that we need to do for the comparison, for selecting, for taking each element out of the unsorted part, and then we compare it with the sorted part, each of those elements till, and we compared it till we reached the value 0. That is, we compared with each of the elements of the sorted part. Now, if one of the element itself and that particular, we see that okay, that particular element is less than the number which needs to be put in, or the number which is selected from the unsorted part, we need not to carry forward into the comparisons of the rest of those elements as we saw over here in this particular case. Okay, so this is how the intuition of the insertion sort works. Now let's see it in the flowchart for this algorithm and also the implementation in code for this algorithm. Insertion sort works by repeatedly taking an element from the unsorted part and inserting it at the apt position of the sorted part. The algo maintains two parts, the sublist which is already sorted and the sublist which is unsorted. Swapping is done as and when the element taken from the unsorted part is less than the one of the sorted part which is currently being compared. We take one element from the unsorted part and compare it with the rest of with all the elements of the sorted part till the point we get into the right position for that element to be inserted. Now points to ponder: the time complexity of the insertion sort algo is O(n) square, and the best case complexity however is O(n). If the list is already sorted, then it will not be doing the comparisons with the sorted part elements. Just one comparison would be made, and therefore the time complexity will come down to O(n). This occurs when an element is to be inserted in an already sorted array. Now, with the already sorted array means that it's in the ascending order as per the current implementation. If the array would have been in the descending order, then that would bring out the worst case complexity. So let's start with the flowchart here. So we have the unsorted list. We take the length of it and we go in from I equals to 1 till I is equal to n minus 1. That is, I is less than n, which, and this I here is denoting the iterations that we are doing for each of the element of the unsorted part. So for the unsorted part, we saw that okay, we take the element from the index position 1 because the element at the root position we take it as already sorted, and then from index position 1 we go until the end of the unsorted list, so which will go till n minus 1 index. Now, for each iteration, we take that particular element index to insert. So at the start, we take index uh, wherein that element needs to be inserted is equal to the current element itself of the element position itself, which is denoted by the first element of the current unsorted part. So we take index to insert is equal to I, and then this particular loop, if j is greater than equal to 0, is denoting the one of the sorted part, wherein we are comparing each of the element which we have taken from the unsorted part to each of the elements of the sorted part. So j is the one denoting the sorted part, and we go from the end index of the sorted part till the 0th position, right? So therein we have the j, which is denoting that. And here we see if x of j, that is the element of the sorted part which is currently being compared, if it is greater than the one which we have taken out from the unsorted part, if it is greater, then that means the one element one which we have taken out from the unsorted part, it needs to be inserted before this particular element of the sorted part, and hence there is a swap that happens, and we set the index position wherein the element needs to be inserted as equals to j, and then we basically minimize the value of the counter j is equal to j minus 1. That is, we now compare it with the previous element of the sorted part, and we keep on comparing till we get j equals to 0. That is, we have compared the first element of the sorted part as well, first part of the entire index, which is also the first element of the sorted part. And this is how the flowchart goes in. And now let's see at the implementation. Now here, the insertion sort implementation is being done here. So we take the length of the list X, which is the unsorted list, and we go in from the range 1 to n, that is which is denoting the unsorted part, and we have the index to insert is equal to I, and j is equal to I minus 1, which is what we have initialized it with. Then while j is greater than equal to 0 and j is equal to I minus 1. Why? Because uh, the ith value of the first element of the unsorted part, and the previous element is the element of the sorted part, right? So j is equal to I minus 1, and j is the element of the sorted part to which we'll be making this first comparison, right? So which is just behind the element which we have taken out from the unsorted part. So while j is greater than equal to 0, that is what we will be doing, and we will see if x of j, that is the element of the sorted part, if it is less than the index, less than the element which we are taking out from the unsorted part, then we will break, then we will do a break. If it is not, that is, if x of j, the element of the sorted part to which we are comparing the element taken out from the unsorted part, if this is not true, then we basically do the swap, wherein x of j and the element which we have taken out from the unsorted part, that those will be swapped, and we will put in the, we will make the value of insert to insert, index to insert equalize to j, and again we'll reduce the counter, and we'll go that in a, do that in a loop till all the comparisons have been done with the sorted part. And at any, while the comparisons are being done with each of the element of sorted part, if at any position we see the sorted parts element is now less than the incoming element, then we will break out of it, right? Because we need not to proceed further with the comparison, as the sorted part is already a sorted section. So this is how it's implemented. Now if you want to run, there are some of the test cases which we can run, and this is the output that you will be getting in this particular GitHub file. The link of this GitHub file is also mentioned in the description of this particular video. Now let's look at one of the test cases here. So here we have 2010, 2030. This is the unsorted list that has been given to us. So it is the insertion sort which is applied. So at first instance, first iteration, it takes the first element to be a part of the sorted, to be one of the element of the sorted part, and the unsorted part is 10, 20, 30, that is the rest of the list. Now what happens is iteration 1 comparing 20 and 10. So 20 is the sorted part, 10 is the unsorted part. We compare both of these. If 20, which is here, if it is greater than 10, then basically we will, 20 is greater than 10, then we'll swap it because 10 deserves a position previous to 20 then. So there's a swap that happens. So 10 and 20, the elements at position 1 and 0 are swapped, right? So 10 is at the position 1 and 20 is at position 0. And then we proceed further. So we have the list now. The sorted part becomes 10, 20. The unsorted part is 20, 30, which is remaining. Now again, we will take 20 out of it, 20, and we'll compare it with both 20 and 10. So we compare with 20 and 20. So 20 is not less than 20 because it is equal to, then again the swapping would happen. So position 2 and 1 are swapped. And then at iteration 2, we compare 10 and 20. So now herein the element which is here 20, which is incoming element, and 10 which is there. So 10 is already less than the element which is incoming, so we will not do any swap. So the list becomes 10, 20, 20 and 30. And now since there's only one element which is left, which would have already, which basically now we need to compare it with 20 and 30. So how does 30 compares with 20? 30 is greater than the value 20 of the sorted part. So there's no swapping being done, and we will just place the element at this particular position, or the assumption of where the element needs to be inserted was true, it's not been violated, and it remains at the same position which it was designated to at the start of the iteration. So this is how you will be able to get all the print statements in order to help you understand how the algorithm is performing. Now, since we have gone through this session, so please try to implement this algorithm on paper. Try to see if you are able to write the implementation code as well. In case you face any issues, please do reach out to me. I hope this session has been useful to you. Thank you.